I've been doing some work on black holes recently, which I hadn't started last time I saw you, actually. So I got interested in it. And the amount of the progress that's been made in trying to understand how they work. And a question that was posed by Stephen Hawking a long time ago, really 1970s, early 1980s, which is what happens to stuff that falls in. But the simplest question you could possibly ask.
Right.
There's progress being made on that now, which I think is profound and exciting.
How is the progress being made? Like how do we study a black hole?
I mean, it's mainly theoretical, although we have now got photographs of them. So we have 2 photographs, which are radio telescope photographs.
Right.
One of the one in the center of our galaxy, which is a little one. It's called Sagittarius A star. It's a little supermassive black hole. So it's about 6 million times the mass of the sun, which makes it a little supermassive. And then there's another one, the first photo that was taken. It's a collaboration called Event Horizon. And they took a photo of one in the galaxy M87, 55 million light years away. That thing is around 6 billion times the mass of the sun. I mean, imagine that, 6,000 million times more massive than our sun.
Is that the largest black hole we've ever discovered?
No, there are bigger ones than that, but that's that's the scale of them. It's a big-ish one, that. But if you think about it, I mean, so there's a number. It's called the Schwarzschild radius of the thing. So if you took our sun, which you can fit 1 million Earths inside, and collapsed it down to make a black hole, it would form a black hole when it shrunk within a radius of 3 kilometers, about 2 miles. So you've got to take this thing, which is what I have to convert from kilometers to miles, don't I? But it's about
that's okay. Just say kilometers.
700,000 kilometers. So it's about 500,000 miles radius or something like that. The sun. So you squash it down till it's about 2 miles, and then that would form a black hole.
Wow.
The 6 billion times the mass of the sun means you multiply that by 6 billion. So these things, the so-called Schwarzschild radius is, I don't know, larger than our solar system. Basically, this thing that sits in a galaxy. So we've got these 2 photographs.
Larger than our solar system.
Yeah, the event. Right, so it's a big structure.
Oh,
that's a Chandra X-ray image of. There it is. That's it. So the that one there. That's the M87 black hole. So what you're seeing there is the emission from the material that's swirling around it. It's called the accretion disk. So you have material that's orbiting very fast, emitting a lot of radiation, and that's what you see. It's a flat disk, by the way. So you think Saturn's rings. So this material is very flat. But what you're seeing in that photograph is the light rays being bent around the black hole from that flat disk. So that was a prediction from Einstein's theory, basically. He published it in 1915. And you can predict that that's what one should look like. And then just about, was that 4 years ago now, maybe 5 years ago, for the first time in history, we get an image of one, and it looks like the prediction. So It's a remarkable thing.
How phenomenal is that?
Yeah. So we've had those 2 photographs. The other thing we've had is so-called gravitational wave detections. So these are colliding black holes, and they collide and merge together. And obviously that's quite a violent event in the universe. And so that event, that process ripples space-time. So it sends ripples out in the fabric of the universe, space and time. And actually Kip Thorne, I've spoken to him several times. He's one of the greats, right? Won the Nobel Prize for this. And he calls it a storm in time. So you get a time storm. So really, we're to think, as we speak now, there will be these very tiny ripples from violent cosmic events passing through this room. And they're changing the rate that time passes. So that as they go through. And we can detect that now. So we have detectors that can pick that up. And so we've seen those collisions as well.
So these collisions, how far away?
Oh, millions of light years away.
And they're affecting what's happening in this room right now?
Yeah, to a tiny extent. So there's an experiment called LIGO, which is the, what it stands for, something like gravitational interferometer. I can't remember exactly what but so basically it's laser beams. And there's one in Washington State, north of Seattle, and one in Louisiana. And they're kind of laser beams, 4-kilometer long laser beams at right angles. And they can detect these very tiny shifts in the effectively, you could say the length of the laser beam. It's a bit more fiddly and complicated, but it essentially measures the distortion in space-time caused by these ripples. And it's way less than the diameter of an atomic nucleus, by the way. Way less. These little sort of...
Oh, my God.
And so we've observed many of those collisions. There it is. There's LIGO. So it's just basically two laser beams, but with these ultra-high precision thing. And so we've got data now of the collision of black holes and those event horizon pictures with radio telescopes. So that's part of it. But the main bit has been theoretical advances in understanding exactly... in a sense, it was what's wrong with Stephen Hawking's calculation, which is a weird thing to say sometimes because people think Stephen Hawking surely didn't get his math wrong. But he did, actually, in his calculation. So what he calculated back in 1973, 1974, is that a black hole... So we picture this thing from which nothing can escape, even light. So when you go in, you're gone, basically. What he calculated is that even though these things are just a distortion in space and time, that's the description of them. So it's almost as if there's nothing there apart from a distortion in space and time. He calculated that they glow, so they have a temperature. So they emit radiation. It's called Hawking radiation. And so important was that discovery. If you go to Westminster Abbey in London, look on the floor of the Abbey on his memorial stone, and he's in there next to Newton and Shakespeare and all these people, and he's there. And chiselled in stone on the floor of Westminster Abbey is his equation for the temperature of a black hole. So it was this tremendously important discovery. So he discovers these things glow, and he calculates how they glow. A very low temperature, but they emit things, which means that they shrink because they're emitting stuff, and so they're shrinking. So that means they have a lifetime. So first of all, one day they'll be gone. So that means that you have to address this question of what happened to all the stuff that fell in. And his calculation said that there's no record at all of anything that fell in all this radiation that's come off the black hole. So it's purely information-less radiation. So what that means is that black holes destroy information, according to that calculation. And that's a big deal because nowhere else in all of physics does anything erase information from the universe. So it's really true that if I got this notepad and pen, right, and I wrote some things on it, and then I set fire to this, even just incinerated it, put it in a nuclear explosion, whatever. In principle, according to all the laws of nature that we know, if you collected everything that came off, all the radiation, all the bits of ashes and things, and you could just measure it all, then just in principle, the idea is you could reconstruct the information. So it all gets scrambled up and thrown out into, and so in practice you can't do it. But just in principle, the laws of nature say that information is not destroyed. It's just scrambled up in a way that you can't reconstruct, right? But this calculation that Stephen did said there is no information in that radiation at all. Zero, just nothing. So it seemed that uniquely in the universe, black holes erase information.
When you say there's no information, like how are you measuring whether or not there's information in it?
So really in bits. I mean, the idea is, and I should say it's very much in principle this. So no one thinks in practice you could reconstruct what I wrote down on this if you set fire to it. But in principle,
well, maybe sometime in the future, maybe a million years from now.
In principle, you could just collect everything. Well, then somewhere in that all that radiation and ashes and light that's come off the thing is the information. It's there. So you could reconstruct the book or what I wrote on this page in principle. But the thing about Stephen's calculation was that even in principle, it said there is no information. And by the way, it's kind of easy to see why, actually, because this radiation, this Hawking radiation that comes off the black hole, it's coming from the horizon of the black hole. So I should say what the horizon is, maybe. So it's if you remember, I said that the sun, if you squashed it down within 3 kilometers of radius, you'd get this kind of distortion in space and time, from which, if you went in across this region 3 kilometers, you went inside it, you couldn't get out. So that's called the event horizon. So you wouldn't notice if you fell through the horizon of the black hole. in the Milky Way galaxy, if you went into that one, we could be falling through that horizon now in this room, and we wouldn't notice anything, except that we couldn't get out again. And ultimately, in a few hours, in that case, time would end for us. So you go to the end of time. We could talk about that. There's a picture of that. Maybe I should talk about this. Is getting quite complicated already, isn't it? We didn't start in a relaxing way, did we? I don't know.
No need to. No need to. Let's get right into it. So we wouldn't notice.
Not for the big black holes. So these supermassive black holes, we could fall across this horizon. It's just like being in empty space for us. So we would just be talking now when we could have been talking on the outside of the horizon, and by the time I finished the sentence we could be on the inside of the horizon, inside the black hole. And according to Einstein's theory, at least, which is the theory that predicted them initially, we could just do that. We could just go in and we wouldn't notice for a bit. The thing we would notice ultimately is you go inexorably, nothing you can do, you go to this thing called the singularity once you've crossed the horizon, and you are going to that thing. And then the question arises, what is that thing? And one answer is we don't know, but in Einstein's theory, it's the end of time. So one way of picturing what's happened here is so distorted is space and time by the collapse of a star or the collapse of loads of stuff to make these big supermassive black holes. We don't quite know how they form, actually, but it's collapsing stuff. So it distorts space and time so much that in a real sense, they kind of flip over. They get mixed up. And so this singularity, which you might have thought of as the point to which this thing collapsed, this infinitely dense point, you might think, but actually it's more correctly to be seen as the end of time, because everything's got mixed up. So you go to the end of time. And it's just like saying, why can't I escape that thing? It's like, why can't we escape tomorrow? Right. So we are going to tomorrow.
Right.
And if I said to you, let's run away from tomorrow, you'd go, I can't run away from tomorrow.
So is it the end of time because all information is being erased? So there's nothing?
Yeah. I mean, is
that the idea?
If you draw the thing, you can draw a map of it, and it just literally time ends. Just purely in Einstein's theory. This is 1915, his theory of general relativity. You just get a line there, a line that says there's no future beyond this line. It just stops.
Okay.
So, I mean, admittedly, that's not... We think there's a lot more to it than that. But
is it just we haven't figured the rest of it out yet?
Well, that's the thing. So we're starting to get hints about what might happen, which is leading us. So to backtrack a bit, why does this calculation Stephen did? Why has it got no information? Why does it say there's no information in this radiation? The thing is, it's coming from the horizon. So it's there's loads of ways to think about it, but one way is that this weird place, this point of no return in space that you can fall through, but it's a point of no return. It sort of shakes, it almost disrupts the vacuum of space and sort of almost shakes particles out of the vacuum. That's one way of thinking about it. But this radiation is coming from the vacuum. It's coming from empty space. Whereas if you think about the thing that I throw in, if I throw this notepad into the thing, then that goes to the singularity. It's got nothing to do, the radiation's got nothing to do with this thing. This thing is not set on fire or something like that. It's gone to the end of time, and just whatever's happened to it has happened to it. So this radiation's got nothing to do with anything that falls in at first sight, at least. And so that was the paradox. It's called the black hole information paradox. It's like it's one way to put it is the laws of nature that we use to calculate what happens tell us that information is never destroyed. And when you calculate what happens, it tells us that information is destroyed. So that's why everyone got interested in it in the 80s, because it's interesting.
There's a supermassive black hole at the center of every galaxy.
Yeah.
But there's also other black holes that aren't necessarily in the center of galaxies.
Yeah, so these little ones were little, they're a few times the mass of the sun. And they're from collapsed stars. So they are stars at the end of their life. Very bigger than the sun, more massive than the sun. But they run out of their fuel, and they start to collapse because gravity squashes them. And if they're sufficiently massive, then there's nothing that can stop the collapse. And so they collapse, as far as we know, to a point, right? And essentially an infinitely dense point. We don't really know what happens we don't know what happens right in the middle. But they collapse to such an extent that there's a region around it from which light can't escape. And so nothing can escape. And that's a black hole.
And what happens to them? Do they travel? Are they moving through space?
Yeah, they're still stars,
right?
So they're still there. They're surrounded this region where if you fall in, it's called the event horizon, and if you go across that horizon, then you are going to the center. There's one way of thinking about it, which is quite cool, which is that the time and space sort of flip is one way to think about it. So in the same way that we are going into the future now. So we're going to tomorrow. There's nothing we can do about it. We are going to tomorrow. In the same way, if you fall in across the event horizon of a black hole, you are going to the middle, the singularity it's called. So that's your future. Every line of your future points to the center of the black hole. So it's kind of the ultimate of no escape, the ultimate prison. You're going to get squashed to an infinitely dense point.
Not every star becomes a black hole at the end of its life?
No, because if something like the sun,
we have a small star.
It's quite small, yeah. And when it collapses, there's a sort of a pressure, a force, if you like, which is caused by the fact that electrons don't like to be very close to each other. So it's called the Pauli exclusion principle. But essentially what happens is that, so as they get squashed closer and closer together, they move faster and faster to sort of get out of each other's way, if you like. And that makes a force which holds them up. And so that creates what's called a white dwarf star. So you can have a blob of matter. They're about the size of the Earth, but they're about the mass of the sun. And so that's for smaller stars. They end up as these white dwarf things, which are very dense objects. There's another version, which is called a neutron star, which is the same thing, but for neutrons. And they move faster and faster. So if it's massive enough that it overwhelms the electron thing, then the electrons sort of crush into protons and turn into neutrons, and the whole thing starts again. And so a neutron star can be, at least 1.5 times the mass of the sun, let's say, but it can be about 10 miles across. So that's an incredibly dense ball of matter held up by the neutrons moving around. It's got a fancy name. It's called neutron degeneracy pressure, but that's what it is. But if you go even bigger, then even that can't hold it up. And as far as we know then, there's no known force that we know of that can hold the thing up if it's too massive. And so that's when it just almost winks out of existence, if you like. It collapses and collapses and collapses. And that's when you get a black hole.
We try to put that into perspective. The sun is 1,000,000 times bigger than the Earth.
Yeah.
And this neutron star is, would you say, 1.5 times the mass of the sun, but 10 miles wide?
Yeah. So, and there's loads of those around. They're called pulsars. So we see those all over the place. The first one that was discovered was called LGM1 because they spin very fast. And it was called LGM1 because it's a very regular pulse, and they thought it was little green men. So they called it kind of jokingly Little Green Men 1. And so, yeah, we've seen that there's one called the Crab Pulsar, which is in the Crab Nebula, which we saw the supernova explosion. So that's when one of these stars explodes at the end of its life and then collapses to form a neutron star. And we saw that in 1054 AD.
Wasn't there some speculation that our solar system at one point was a binary star system, and that one of those stars had become a dwarf?
I don't know.
Someone had read something about that in relationship to the dense object they believe is outside the Kuiper Belt.
Yeah, I mean, there's some evidence. There's a bit of evidence that there's something out there. Yeah. Because of the periodic extinctions and things on Earth, like you get periodic bombardments from out in the Kuiper Belt. So yeah, I think one of the theories is
periodic extinctions.
Well, yeah. So for example, like there have been mass extinctions on Earth when a lot of the life died, and we don't know what caused all those, but sometimes they're impacts from space. That seems clear. And so, yeah, there are theories that there's something orbiting out there which can disrupt all these objects out in the Kuiper belt that sends loads of comets and asteroids inwards to the inner solar system and can cause havoc. And so there's some people look at those theories.